How to Study Mathematics for Teens. Episode 1, The History of Mathematics. Hey there, future mathematicians. Welcome to How To, where we'll embark on an exciting journey through the fascinating history of mathematics in our series on studying mathematics for teens. Let's discover the fascinating world of mathematics. Big picture. Our exploration is divided into 4 captivating parts, each unveiling a different epoch in the history of mathematics. Part 1, Ancient Mathematics. Segment 1, Mesopotamian Mathematics. Unearth the mysteries of ancient Mesopotamia, where clay tablets bore the first inklings of mathematical notation. We'll delve into the foundations of basic arithmetic etched in the cradle of civilization. The 2 main topics include 1. Overview of cuneiform tablets and early mathematical notations. 2. Babylonian mathematics and sexagesimal, the base 60 numeral system. Segment 2. Egyptian Mathematics. Journey to the land of the pyramids, where the Egyptian number system and hieroglyphic representations played a crucial role, not only in construction, but also in the study of the cosmos. The 2 main topics include 1. Explanation of the Egyptian number system and hieroglyphic representations. 2. Highlighting the use of mathematics in construction and astronomy. Segment 3. Greek Mathematics. Sail through the Mediterranean waters and explore the birthplace of geometry. From Pythagorean wonders to Euclidean foundations, the Greeks left an indelible mark on the mathematical landscape. The 2 main topics include 1. Introduction to Pythagoras and the Pythagorean theorem. 2. Overview of Euclid's elements and the foundations of geometry. Part 2. The Middle Ages and Islamic Golden Age. Segment 1. Indian Mathematics. Take a detour to ancient India, where the decimal system was born. Discover the brilliance of Indian mathematicians and their contributions to algebra and trigonometry. The 2 main topics include 1. Introduction to Indian numerals and the decimal system. 2. Overview of contributions to algebra and trigonometry. Segment 2. Islamic Mathematicians. Venture into the Islamic Golden Age, where scholars like Al-Khwarizmi paved the way for algebra. Witness the House of Wisdom and the incredible translation movement. The 2 main topics include 1. Highlighting the work of Al-Khwarizmi in algebra. 2. Introduction to the translation movement and preservation of Greek texts. Segment 3. Fibonacci and the Italian Renaissance. Fast forward to the Italian Renaissance, where Fibonacci introduces us to his famous sequence. Join us as we unravel the mathematical wonders of the Renaissance. The 2 main topics include 1. Explanation of Fibonacci sequence and its applications. 2. Overview of the revival of interest in mathematics during the Renaissance. Part 3. The Age of Enlightenment and Beyond. Segment 1. Newton and Leibniz. Step into the Age of Enlightenment, where Newton and Leibniz redefine the mathematical and physical landscape. Explore the calculus controversy and the birth of modern physics. The 2 main topics include 1. Overview of the calculus controversy. 2. Introduction to Newton's laws of motion and universal gravitation. Segment 2. Euler and the Enlightenment. Enter the world of Euler and the Enlightenment, where mathematical ideas blossom. From graph theory to number theory, Euler leaves an indelible mark on mathematics. The 2 main topics include 1. Highlighting Euler's contributions to graph theory and number theory. 2. Discussion of the Enlightenment's impact on mathematics and science. Segment 3. 19th Century Mathematics. In the 19th century, Gauss, Riemann, and Cantor expand our understanding of numbers, space, and infinity. Let's explore their groundbreaking work. The two main topics include 1. Introduction to developments in algebra, analysis, and geometry. 2. Overview of key mathematicians like Gauss, Riemann, and Cantor. Part 4. 20th Century and Modern Mathematics. Segment 1. Einstein and the Theory of Relativity. Fasten your seatbelts as we dive into the 20th century. Einstein's revolutionary ideas changed the way we perceive the universe. Let's explore the connection between mathematics and theoretical physics. The two main topics include 1. Explanation of the relationship between mathematics and physics. 2. Overview of Einstein's contributions to theoretical physics. Segment 2. Computer Age and Information Theory. The computer age dawns and mathematics finds new applications. Discover the role of computers and the fascinating world of information theory. Algorithms, anyone? The two main topics include 1. Introduction to the development of computers and their impact on mathematics. 2. Discussion of information theory and the role of algorithms. Segment 3. Contemporary Mathematics. Our journey brings us to the present, where mathematics is alive and thriving. From cutting-edge research to diverse voices in the field, let's explore the exciting world of contemporary mathematics. Now it is time to delve into the details of the history of mathematics. The main topics include overview of recent developments in mathematics. Hi, all future scientists! Now it is time to delve into the details of the history of mathematics. Welcome to How To, where we'll embark on an exciting journey through the fascinating history of mathematics in our series on how to study mathematics for teens. Our journey begins in ancient Mesopotamia, where humanity first started to make sense of numbers. Imagine clay tablets etched with mysterious symbols. This was the birth of mathematics. Now, before delving into the history and contribution of Mesopotamia to the development of mathematics, let's take a brief look at its history to get a bigger picture of Mesopotamia. Mesopotamia is an ancient region located in the eastern part of the Mediterranean, mainly within the borders of modern-day Iraq, Kuwait, parts of Syria, and Turkey. The historical timeline of Mesopotamia covers a vast period, beginning around 3500 BC and extending through various civilizations until approximately 539 BC. This region is often referred to as the cradle of civilization because of its significance in the development of early human societies. The two main rivers that define Mesopotamia are the Tigris and Euphrates. These rivers provided fertile land for agriculture and were essential for the growth of some of the world's earliest civilizations, including the Sumerians, Akkadians, Babylonians, and Assyrians. In the heart of Mesopotamian cities, mathematicians of antiquity didn't have sleek calculators or high-tech devices. Instead, they wielded something far more humble: clay tablets. These tablets, etched with mysterious symbols, served as the canvas for the birth of mathematics. Behold the wonder of cuneiform tablets. These ancient artifacts are like mathematical time capsules. Let's dive into the animations to unravel the mysteries they hold. On these tablets, our mathematical ancestors carved wedge-shaped symbols, creating the world's first known writing system, cuneiform. Each mark represented a numerical value, a primitive yet powerful language that allowed them to communicate mathematical ideas. But what were they calculating on these tablets? It wasn't complex calculus or advanced algebra, but the fundamentals of arithmetic. Mesopotamians were masters of basic calculations, from addition to multiplication, using their unique numerical system. Not only that, here's another fascinating fact we need to remember. Babylon was one of the prominent cities in ancient Mesopotamia. Babylon, an ancient city in Mesopotamia, held a prominent place in human history as a cultural, political, and economic center. Located on the Euphrates River in present-day Iraq, Babylon flourished under the rule of notable leaders like Hammurabi, who established the famous Code of Hammurabi. The city boasted impressive architectural achievements, including the Hanging Gardens, one of the 7 wonders of the ancient world. Babylon was a hub of trade and cultural exchange, connecting diverse civilizations in the ancient Near East. Babylonian mathematics is a subset of Mesopotamian mathematics. Its mathematical contributions, such as the base 60 numeral system, are noteworthy. The Babylonian numeral system had a positional notation system similar to our base 10 system, but with the base being 60. They used a combination of wedge-shaped marks on clay tablets to represent numbers. This system had practical advantages for the Babylonians in the context of astronomy, timekeeping, and other mathematical applications. If you carefully examine the Babylonian number system in the picture, you will notice that the numbers range from 1 to 59 and are all written in a unique pattern. This is because, unlike our base 10 decimal number system, the Babylonians used a base 60 number system. Numbers like 12, 24, 60, and 360 are closely related to the Babylonian number system in their origin. You might then wonder, does the Babylonian number system have anything to do with our modern life? The short, simple answer is yes. For example, we use both the 12-hour and 24-hour time systems. 1 hour is 60 minutes and 1 minute is 60 seconds. A year is divided into 12 months, and a circle is measured in 360 degrees. Here's a breakdown of the significance of the numbers in the Babylonian base 60 system. 12. The number 12 is a significant divisor of 60. Babylonian mathematics often used a base 60 place value system, which means that 60 had special significance. 12 is a divisor of 60, so it's a convenient number for dividing the year, the day, and other time-related quantities. 24. The number 24 is also related to the base 60 system. It's twice the number 12 and is used in various time-related calculations. For example, a day was divided into 24 hours, each hour into 60 minutes, and each minute into 60 seconds. 60. The number 60 is the base of the Babylonian numeral system. It's a highly composite number, meaning it has many divisors, including 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, and 60. This made calculations more manageable for the Babylonians, especially in the context of measuring time and angles. 360. The number 360 is significant because it's a multiple of both 12 and 60. It's often associated with the measurement of angles in Babylonian mathematics. A circle was divided into 360 degrees, a tradition that continues in modern geometry. Now let's head to the land of the pyramids. Egyptians not only built unbelievable buildings and structures, but also had a unique way of counting. Get ready to explore the secrets of the Egyptian number system. Ancient Egypt, a civilization that flourished along the banks of the Nile River, is renowned for its rich cultural legacy and enduring contributions to human civilization. Here is a brief history of ancient Egypt. Emerging around 3100 BC, the civilization began with the unification of Upper and Lower Egypt by King Menes, Narmer, marking the onset of dynastic rule. The Old Kingdom, 2686 to 2181 BC, saw the construction of monumental pyramids at Giza, symbolizing the pharaoh's power and the afterlife's significance. This period showcased a centralized government, advanced agricultural practices, and a thriving economy. The New Kingdom, 1550 to 1070 BC, marked a zenith for ancient Egypt, characterized by powerful pharaohs such as Thutmose III and Ramses II, military conquests, and a prolific period of cultural and artistic achievements. The Valley of the Kings became the burial ground for pharaohs, adorned with intricate tombs and artifacts. However, internal strife, invasions, and periods of decline followed. Egypt's history continued through the late period and Ptolemaic and Roman rule, witnessing cultural blending and the famed Queen Cleopatra. The conquest by Arab Muslim forces in 642 AD marked the end of ancient Egypt, but its legacy endures through its contributions to science, architecture, art, and the enduring fascination with its mysteries. Now, it's time to delve into the wonders of Egyptian mathematics. Are you ready? Picture towering pyramids that defy both time and gravity. But beyond their architectural grandeur, the Egyptians left us with a legacy of numerical brilliance. Let's observe the hieroglyphs, each symbol holding a distinct numerical value. From simple strokes to elaborate depictions, the Egyptians ingeniously expressed numbers using a language of images. As we step into this ancient world, be prepared to decipher more than just the hieroglyphics decorating temple walls. The Egyptians had a unique way of counting, a numerical system as captivating as the stories etched in their tombs. But Egyptian mathematics wasn't confined to mystical symbols. It played a crucial role in the construction of those towering pyramids. The precision required for such monumental feats involved intricate calculations. Ancient Egyptian mathematics is an intriguing aspect of the civilization's intellectual achievements. The Egyptians developed a sophisticated system of mathematics that was primarily practical and applied to various aspects of their daily lives, such as agriculture, construction, and trade. The Egyptians used a base 10 numeral system, which means it was based on powers of 10. The following hieroglyphs were used to denote powers of 10. Ancient Egyptian texts could be written in either hieroglyphs or in hieratic. In either representation, the number system was always given in base 10. The number 1 was depicted by a simple stroke. The number 2 was represented by 2 strokes, etc. The numbers 10, 100, 1,000, 10,000, and 100,000 had their own hieroglyphs. Number 10 is a hobble for cattle. Number 100 is represented by a coiled rope. The number 1,000 is represented by a lotus flower. The number 10,000 is represented by a finger. The number 100,000 is represented by a tadpole. And 1,000,000 was represented by a god with his hands raised in adoration. Ancient Egyptian mathematics is an intriguing aspect of the civilization's intellectual achievements. The Egyptians developed a sophisticated system of mathematics that was primarily practical and applied to various aspects of their daily lives, such as agriculture, construction, and trade. Here are several examples of how the ancient Egyptians applied their mathematical knowledge in practical contexts. Land measurement. The ancient Egyptians used geometry to measure and divide land for agricultural purposes. The use of geometry and surveying techniques helped in maintaining fair and consistent land distribution. The annual flooding of the Nile River required accurate measurements to re-establish property boundaries after the floods. Construction of the pyramids. The construction of the pyramids is a remarkable example of the Egyptians' mathematical prowess. They employed advanced geometric principles to ensure the precise alignment and dimensions of the pyramid structures. The sides of the pyramids, for instance, were built with careful consideration of angles and proportions. The Rhind Mathematical Papyrus. This ancient mathematical document contains numerous problems and solutions. For example, one problem involves calculating the volume of a cylindrical granary. The Egyptians used a formula equivalent to the modern formula for the volume of a cylinder, demonstrating their understanding of geometry and practical mathematics. Trade and commerce. In their everyday commercial activities, ancient Egyptians demonstrated a sophisticated use of arithmetic, employing it to calculate prices, negotiate transactions, and maintain accurate records of trade. Their well-developed system of weights and measures for various commodities, including the use of tools like scales and measuring rods, ensured fairness and transparency in transactions. The importance of fractions, particularly unit fractions, was evident in the precise division and distribution of goods for trade, allowing merchants to manage portions equitably. The hieratic numeral system further facilitated efficient record-keeping, enabling merchants to document quantities, prices, and other essential information. This mathematical prowess not only supported day-to-day transactions, but also contributed to the development of extensive trade networks, economic prosperity, and the overall influence of ancient Egyptian civilization in the ancient world. Calendar system. The Egyptian calendar was based on astronomical observations, and its development required mathematical calculations. They divided the year into 12 months of 30 days each, with an additional 5 or 6 epagamenal days. This calendar system helped in agricultural planning and religious observances. Here is the calendar in the Temple of Kam-Ambo. The calendar shows the hieroglyphics for the days of the 4th month of the harvest and the 1st day of the 1st month of the flood. Architectural precision. The construction of the pyramids, temples, and other structures required careful mathematical planning. The Egyptians used geometry to ensure the alignment and symmetry of columns, walls, and other architectural elements. This precision is evident in the layouts of temples like Karnak and Luxor. These examples highlight the Egyptians' practical application of mathematics in various aspects of their civilization. The combination of arithmetic, geometry, and measurement allowed them to excel in fields ranging from agriculture and trade to monumental construction projects. The next chapter of the series on how to study mathematics for teens awaits, where we'll journey through more mathematical landscapes. Until then, keep the spirit of Egyptian ingenuity alive in your mathematical explorations. Greetings, daring adventurers. Embark on a mathematical journey as we cruise towards the vibrant coasts of ancient Greece, where the sun-kissed vistas gave rise to not just philosophers and poets, but also the cornerstones of geometry. Get ready to navigate the seas of mathematical enlightenment with Pythagoras, Euclid, and the captivating mysteries of triangles. As we sail through the Mediterranean, we arrive in ancient Greece, the birthplace of geometry. The deep blue Mediterranean stretches out before us, carrying whispers of ancient wisdom across its waves. Ancient Greece is a land where philosophy and mathematics intertwine, a realm where thinkers endeavored to unveil the secrets of the cosmos. Pythagoras, Euclid, and the mysteries of triangles await us. First, our journey begins with Pythagoras, a mathematician and mystic, whose theorem remains one of the most famous in history. Have you ever wondered who Pythagoras was? Pythagoras, a renowned ancient Greek mathematician and philosopher, is best remembered for the Pythagorean theorem, a fundamental principle in geometry. Born around 570 BC on the island of Samos, Pythagoras founded a religious movement known as Pythagoreanism, blending mathematical insights with spiritual beliefs. He and his followers made significant contributions to mathematics, exploring the properties of numbers, geometric shapes, and the relationships between them. Pythagoras' theorem, denoted by a squared plus b squared equals c squared, is a foundational principle in geometry, attributed to the ancient Greek mathematician Pythagoras. This theorem reveals a fundamental relationship within right-angled triangles. The square of the hypotenuse's length equals the sum of the squares of the other two sides. In addition, Pythagorean mathematicians discovered a groundbreaking fact. The square root of certain numbers is irrational, signifying that these numbers cannot be expressed as simple fractions. For example, the square root of 2 is 1.4142, 1356237, and continues indefinitely. This challenged the prevailing notion that all numbers could be represented as ratios of integers. Thus, the concept of irrational numbers was newly discovered. Beyond its simple expression, the theorem is a powerful tool with widespread applications in fields like physics, engineering, and navigation. Its elegance and versatility make it an enduring cornerstone of mathematical understanding, providing essential insights into spatial relationships and serving as a basis for solving diverse real-world problems. Pythagoras' theorem stands as a timeless and essential concept, influencing our comprehension of geometric relationships. It remains a cornerstone in modern mathematics with far-reaching practical implications across diverse disciplines, such as music, astronomy, and philosophy. In doing so, it leaves an enduring legacy that enriches human civilization. However, our Greek adventure doesn't stop there. Here comes Euclid, who is often hailed as the father of geometry. His masterpiece, Elements, is a timeless treasure trove of mathematical knowledge. Then, have you ever wondered who Euclid was? Euclid, a Greek mathematician, lived around 300 BC and made profound contributions to the field of mathematics. His most influential work, Elements, is a comprehensive compilation of knowledge in geometry and number theory, consisting of 13 books in total. Euclid's deductive approach and logical structure in Elements set the standard for mathematical rigor for centuries to come. His theorems, definitions, and postulates form the basis of Euclidean geometry, and his work played a pivotal role in shaping the study of mathematics in antiquity and beyond. Then, what are Euclid's theorems, definitions, and postulates? Theorems. Theorems are like the special tricks or secrets that Euclid discovered about shapes. For example, one of his theorems says that in a right-angled triangle, the square of the longest side, called the hypotenuse, is equal to the sum of the squares of the other two sides. Another theorem might tell us how the angles in a triangle add up to 180 degrees. These theorems are like the special rules that shapes follow, and they help us solve all sorts of geometry puzzles. Definitions. Definitions are the ways Euclid gave names and descriptions to different types of shapes. For instance, he defined a circle as the set of all points in a plane that are a certain distance away from a center point. These definitions help us talk about shapes without getting confused. If we know the definition of a square, for example, we can identify it and understand its properties. Postulates. Postulates are like the basic rules that Euclid believed everyone could agree on without needing much explanation. One of his postulates says that you can draw a straight line between any 2 points. Another one might say that all right angles are equal. Postulates are the fundamental ideas that serve as the starting point for understanding geometry. They are like the agreed-upon rules of the game. So, thanks to Euclid's theorems, definitions, and postulates, we have this incredible toolbox to explore and communicate the enchanting world of shapes and geometry. They are the building blocks that unlock the secrets of triangles, circles, and all sorts of other geometric wonders. Euclid's legacy endures not only in the realm of mathematics, but also in the broader impact of his systematic and logical approach to knowledge, which has influenced various branches of science and philosophy throughout history. In addition to Pythagoras and Euclid, Archimedes, Apollonius of Perga, Hipparchus, and Zeno made memorable contributions to the history of mathematics. Let's take a closer look at their discoveries. Archimedes' principle. Archimedes, another influential Greek mathematician, made significant contributions to geometry and fluid mechanics. His principle states that a body submerged in a fluid is subject to an upward buoyant force, equal to the weight of the displaced fluid. This principle is fundamental in understanding flotation and is applied in designing ships, submarines, and other floating structures. Coordinate geometry. Apollonius of Perga, a Greek mathematician known as the Great Geometer, contributed to the development of coordinate geometry. Today, coordinate systems, where points are located using pairs of numerical coordinates, are extensively used in various fields, including physics, engineering, and computer science. Trigonometry. The Greeks, particularly Hipparchus, made significant contributions to trigonometry. Trigonometric functions such as sine, cosine, and tangent are used extensively in various scientific and engineering applications, including physics, architecture, and computer graphics. For instance, trigonometry is crucial for calculating angles, distances, and waveforms. Infinity and limits. Zeno's paradoxes were a series of philosophical problems posed by the Greek philosopher Zeno of Elea. They led to discussions about the concept of infinity and the idea of limits. These discussions laid the groundwork for the development of calculus, a branch of mathematics essential in understanding rates of change and accumulation, with applications in physics, economics, and engineering. In conclusion, the emphasis on rigorous proof and logical reasoning in Greek mathematics has profoundly influenced the contemporary approach to mathematics. Furthermore, concepts such as theorems and postulates introduced by the Greeks continue to serve as fundamental building blocks of modern science. Finally, we have reached the end of the first part of our mathematical journey, the history of mathematics for teens. Great work, everyone. Until we meet again for the second part of History of Mathematics, the Middle Ages and Islamic Golden Age, in How To, take care of yourselves.